Good morning, everyone, and thank you for joining us for this session of Webcast Wednesday, the June's special version. I'm Omid, and I have the pleasure of hosting today's session, and we're going to go over dealing with imbalanced datasets in machine learning today. So let's get started. And hopefully you guys can see my screen. So today we'll be talking about how to work with imbalanced datasets and how to train a machine learning model, a classification model, a regression model, anything with imbalanced datasets and actually get useful results from that. So, like I said, welcome and thanks for joining us. I know it's early in the morning for some people and quite late in the evening for others. So I appreciate you being here with us. Real quick, a little bit about myself. My name is Omid Meh. I am a developer advocate at IBM. And right now I'm finishing my master's in data science. I have 2 bachelors as well, software engineering and electrical engineering. And I have years of experience in software development before moving to data science. Specifically, before starting my data science journey, my focus was on DevOps, automation, which is near and dear to my heart, and also security. So if you guys have any questions in those areas or now data science, feel free to find me on LinkedIn, on my IBM's profile, on GitHub. Just reach out to me and I'll be glad to have a chat. The topic of security actually brings me to a nice plug for the events for the conference that my team is hosting. So we've put together, as IBM in general, a cloud native security conference. That's a 5-hour conference free of charge, held by experts in IBM and Red Hat, all subject matter experts. And it will be run in 4 different regions and 3 different days, so you could join in your convenience. And it has 3 different tracks. It has the application security. So if you're trying to create applications that you're going to run on cloud and you want to know how you can secure it, it has content for you. It has data security, which actually nicely ties into today's session because we're going to be talking about data. So there's a whole track on data security, and then there is an entire track on DevSecOps, which is the practice of bringing security to your DevOps pipelines. They're all very interesting topics, and they're all very useful content. So if you have the chance, I would highly suggest you joining them for as many tracks as you can, and just at least sitting in and seeing what they're talking about and learning some good, useful information, especially that is free and it's held by people, like well-seasoned people who've been in the field for many years. Now, I know you're super hyped about it and you want to know how to get to it, so that's the link on the bottom. If you want to find the Cloud Native Security Conference, either search for it, Cloud Native Security by IBM Developer, or go to ibm.biz/devcon-security. And if you have questions, let me know. So a little bit of background as to why we are here and why we're having this conversation to begin with. As we all know, data science starts with data. Without data, we won't have any models. Without data, we won't have any insights coming from our models. And without without the data, we can't infuse any useful insight into our application or business processes to improve it. So we need to take care of our data, and we need to make sure it's good and nice and clean. And it kind of sort of ties back into the whole concept of garbage in, garbage out, right? If you have the best model in the world, but we have useless or not clean or data that's not ready to be consumed, and we feed it to our model, we're not going to have a useful insight coming out from the other side. So we have the whole part of we need to make sure the data that you're feeding in is well done. It's a lot of it is about prep work. I won't say all of it is about prep work, but a lot of this whole lifecycle journey is about the data part of it. The other aspect of it is that a lot of data sets are imbalanced just by nature. There are data sets out there that naturally are balanced, but I would say more often than not, you would find data sets that the class that you're interested in or what you're trying to train your regression model for is actually pretty rare compared to the other side, compared to the normal or compared to the class that's not necessarily of interest. And these imbalanced data sets could pose an issue for algorithms. This is not for all algorithms. There are different algorithms are more or less susceptible to skew in the input data. But as a general rule of thumb, you want to remove this skew because it's going to bias your model and it's going to bias your output in a way that you might not want, or at least you want to be aware of it. In most cases, you would want to deal with it in some form or fashion. Now, you might ask, what is an imbalanced data or what is skewed data? So just to put it in a simple terms, it's the case where the class that you're interested in, or not even the class you're interested in, the class that they're within your data set, your labels are not equally or your labels are not similarly distributed. So if you look at this chart that I made on this right side, and I have a lot of these going through the lecture that just made simple data sets, we have a data set that has more than 100 of one class and only about 5 of the other class. This is highly skewed, and if you train classification models on top of this, they're going to be highly biased towards the first class. And I didn't label any of these because it doesn't really matter. It's more of a conversation. It's more of I'm trying to make you understand what the situation is. So if you have 2 or more classes and they are not more or less evenly distributed, that's where we have an imbalanced data set. To put it a little bit more in practice, I'm going to give you some examples of where you would find imbalanced data sets. So let's say fraudulent transactions. If you're looking at credit card transactions and you wanted to find fraud within them, imagine how many non-fraud transactions are there for every one fraud, right? It's not as if that you're going to have a 50-50 split of transactions that are fraudulent and non-fraudulent. So that would be a case where if you just blindly train a classification model on top of it, it's going to be really good at telling you that pretty much anything that comes its way is not fraudulent. And we'll talk about this later in terms of the metrics, but if you were going to just look at its accuracy, right, it could just purely memorize that all the transactions are not fraudulent. It would probably be more than 99% of the times right. It would just, whatever you tell it, it's just whatever input comes in, return not fraudulent. It would be 99% of the time right, but it's not all that useful. That's not what we care about, right? So we need to care about we need to adjust this and we need to prepare our data before we take it for our training. Let's say cancer detection. This is one of those cases that you want a high recall, and we talk about this later. But this is a case that you want to know for a fact everybody who has cancer, you want to detect it. And it's fine if you have some false positives. It's fine if we detect some people and we think they have cancer, but they don't, because this is probably going to be a preliminary test. And after this, we're going to send them for a much more expensive test into a lab, and they're going to go through additional screening. So you want to have a test up front that's going to catch everybody who has a cancer and maybe some that don't, but you don't want it to miss anyone because that's going to be costly. It's a lot worse if you miss a person who actually had cancer versus somebody who didn't have cancer and you tell them you might have cancer, but they go through the additional screening and you're like, okay, actually you don't. So that's another case. Let's say customer churn. If you're looking at all the data that you've collected from your customers and you want to predict who's going to churn, who's not going to churn, most of them are not going to churn. So it's going to be an imbalanced data set between the classes of people who churn and people who don't churn. Employee attrition. Most employees don't leave the company, relatively speaking. So you need to, again, adjust for this skew in the data to be able to get a classification or prediction model in this case that could reasonably predict. And this last one has been the latest project I've been working on, which is detecting a drowsy driver when they're driving behind the steering wheel just by video. Most of the time, they're not drowsy. So of the time series frames that you have, more than 99% of the driver is awake and vigilant. So it's not that easy to just be like, hey, here's all the frames or here's all the time series, go learn from them, and it's going to learn from it. It takes quite a bit of adjustment. So just some examples to say that it's out there and it's important and it's not something that's a one-off thing and we don't have to worry about it. More likely than not, in whatever data set you have, there is some skew, and by adjusting it, your model would benefit. So to summarize all the stuff that I said, why are we here? Because imbalanced data sets are everywhere, because they can negatively affect our model quality, and because we want to know what to do about them. So now that we know it's there, now that we know it's not good, let's see what we can do about it. Before we go further, I want to do a little bit of level set of what the session is about and what it isn't about. So first and foremost, what can we do about what can we do about this data skew? I'm going to follow this AI ladder. This is IBM's prescriptive way of how you can approach your AI end to end. It's a simple 4-step ladder. All it says is that you bring your data into whatever system platform that you have. You collect all your data, whether copy them all over, no, don't do that, or have a way of being able to connect to different databases wherever they reside and pull them in. So you do your collection. Then you do data organization part. That's the part that you make sure all your data is clean and ready to be analyzed. That's the step we are going to be covering a part of today. Then you go through analysis. Now that you have clean, ready data, you're going to build your models. And then at the end, you infuse these models insights into your final projects, into your product, business processes, whatever it is. So we're going to go over the data. It's what we're going to talk about is a step in the data preparation part. So it falls under the organized part of the ladder, second step. And we'll go over how you can address these. So now we have a system. We know what part of the system is going to address imbalanced data sets. It's the organization phase. And we're going to go over how to do it. Just to make sure everybody's on the same page, today we are going to do a survey of common techniques that are there to help you deal with imbalanced data sets. There is a lot more of these techniques. There are lots and lots of papers, and probably as we speak, there is more and more being written. And they all have different approaches, and they all have different pros and cons, and they all address a specific kind of data set or a specific kind of skew. So this is not going to be representative of everything that's out there, but it's going to be the more common ones, or at least a good place to get started. We are going to have a hands-on part. I'm going to go over a Jupyter notebook at the end, which I'll give you access. And we're going to go over some of these techniques in that Jupyter notebook. And it's going to be more of a notebook, a conversation style. We explore the data, we train models, we see how it does, we adjust it, we see how it does, we adjust the data, we see how it does. So it'll be a process rather than just here's the final solution, go deal with it. And like I said, today is not going to be about an in-depth study of any of these algorithms. I'll go over some intuitions, and I'll try to give you some feel of how they work and why they work and when you should use which ones. But I'm not going to go over the details of mathematics of it and how they behave under different scenarios. So with that, let's get started and go over the things we're going to discuss for addressing these data imbalances. First and foremost, I'm going to give you the best technique that's out there to deal with data imbalance. I know in pretty much all the videos, everybody keeps the best for the last, so you keep watching the whole video and they bring you along all the way just to give you that final best answer. I'm just going to give it to you up front, so we all know what it is. We can get it out of the way, and we're all friends. We don't need we don't need to keep it all the way at the end just to keep you watching. So we're going to go over the best technique, success guaranteed if you can do it. Then we're going to look at two other aspects. We're going to look at data wrangling, which is adjustments we were going to make to the data. And then we're going to look at different adjustments we can make to the model itself, or how we set up the problem. Now, since this talk is more about data, I'm going to have a lot more details on the data wrangling part, which is going to go over undersampling, oversampling, undersampling with clustering, ensemble of resamples, and the technique called SMOTE. And that's going to be the bulk of what I'm going to talk about in the lecture. And I'll go quickly, one slide each, over how you could approach it differently in terms of problem setup and how you could think about it differently. So let's get to it. Best technique, right there, out front. Collect more data. Nothing beats if collecting more real data to address your data skew. So if you have class imbalances and it's possible, the best thing you could do is if you go out or whatever technique you have and collect more data from the minority class. This is, of course, not always possible and not always feasible, even if it's possible. So I understand that. But just so we all know, whatever we're going to talk about later, all these mathematics and complex techniques and statistical ways of dealing with the model, none of them beat if you can actually collect more data. So really keep it in mind, if it's possible at all, get more data ideally from the minority class. That's going to increase the quality of your model significantly. So best technique out of the way. With that, let's get started. I'm going to show you, this is a sample example that I've created, and I'll describe what it is. But we'll be studying this and what happens to this when we apply different techniques of resampling to see what happens to it. So on the right side, it's just all the data points that I've generated. It's not a big data set. It's about, I think, 250 points total. So it's about 100, no, actually, it's just over 100 data points. And all of this is showing you all the data that I have. We have all these guys on the right side that are one class and all these guys on the left side that are one class. Now, of course, this is not a terribly difficult problem to solve. This is not a terribly difficult, you could probably create a support vector machine, or you could, the decision boundary is pretty clear. So it wouldn't be too difficult, but nonetheless, it will get the point that I'm trying to get across to you, and hopefully it will build intuition. So here's our data set. The way the classes are laid out is you have a huge imbalance on the purple side. So the purples are the majority of the class, and we have 5 yellow points that are our minority class. And we want to see what happens, like how can we adjust these classes to make them more balanced. So these two distributions are a little bit more on the same side, on the same size, so that when we train our classification models on top of it, the classifier can actually do better than just be skewed to guess everything is purple. So you have 100 some data points. They have 2 features. You can see them. And based on those 2 features, they're divided into some different classes, to 2 different classes. Yellows are one class, purples are the other class. So now let's go through some of these techniques that we talked about and see how you can rebalance these data sets. Method 1, random oversampling. This is the case, and we'll go over these details on the left side. But if you just look on the right, from how it looks like when you plot it, there is no difference. All we've done is initially we had 104 purples and 5 yellows, and we oversampled it, meaning we basically randomly grabbed a bunch of these yellows and duplicated them until we reached an equal balance. You don't have to necessarily reach equal. I did it for the sake of example. But if you notice, it doesn't look different when you plot it because all the yellows are on top of the previous yellows. So in some sense, you haven't gained any new information. Not that we could gain any more information without collecting more, but it doesn't seem like anything has changed. However, this is useful for cases where the algorithm learns iteratively, or the algorithm is actually sensitive to the distribution of the skew. So even though it might seem the data hasn't changed, in terms of distribution, we've gone from 104 in one class, 5 in another class, to both being equal number of data points in each class. And this would help algorithms like neural network or stochastic gradient descent. And these are algorithms that are susceptible, that are sensitive to the distribution of your data, to the skew in the distribution of data. It's also helpful with algorithms that are sensitive to your data being balanced. So say random forests or support vector machines, they could get confused and they could get biased towards the purple class if we don't do this duplication or oversampling of the yellows. Now, of course, oversampling is one of the most naive ways of dealing with data imbalance, but nonetheless, it's one of them. Now, some things you need to be worried about and cautious about is by doing this, since you're just adding more and more of some data points, in this case, there's only 5 of them, so it's actually pretty bad. We are going to introduce the risk of overfitting. Once we have so many of these data points, it's very possible that our classification model just learns specifically those 5 models and not what's generic about them and overfit to those. So that's one of the things to be careful about. Now, in a case where you have a lot more data, it's less of a problem, but nonetheless, be cautious of that. And the other thing is it increases training time. We just increase our entire training size, the whole thing, but it implies that we also increase the size of our training set. And that means we're going to need more computation. It's not always a problem, specifically, especially in this case that I have 106 data points. But if you have something that had many data points and you're trying to now oversample the minority class, it might make a significant difference. So I hope you got some intuition about what oversampling is. It's basically grabbing some of your minority class at random and duplicating them, and then using all of that as your training data. The other part is if you go the other way. If instead of increasing these guys, the minority class, we decrease the majority class. And its impact would look something like this. I've applied random undersampling. So at random, I've grabbed some of these purple dots and I've discarded the rest. Now, I didn't do it to reach a 1-to-1. I did it to reach a 2-to-1 ratio, but nonetheless, it's significantly better than it's somewhere around 20-to-1 that we had. So when can it be helpful? In a case where you have enough data points from your majority class and you have enough examples in your minority class. So in a sense that let me start with a drawback actually. The drawback with this is that you lose information when you just discard data points, right? Specifically in this case, something terrible has happened, which is these 4 that are pretty much the outlier from the rest of the cluster has fallen off here. Now, specifically in this case, it's not necessarily a problem, but if I had some extra yellows all the way back here, so if my decision boundary was somewhat of a ring, that would be terrible because I would have lost those data points here and the classifier would never know about them. So just picking something at random without looking at how your data set looks like is not necessarily a good idea, especially if you have some outliers that are important. They're not mistakes. They're actually real legitimate outliers that count as a part of your distribution. You don't want to just randomly undersample them. But if everything looks uniform enough and your majority class looks uniform enough, you could probably randomly grab some, create a random variable based on your majority set and grab some of them at random. But keep in mind the problem with that is, for example, you could lose these important informations here. So let's keep that in mind. Now, how can we deal with that, right? Undersampling by itself is not a terrible thing. The problem is now that by just blindly, randomly grabbing some stuff, we might lose information. So what could we do about it? And you could read more about this. Just look for just search for papers. There's lots of papers on these. But you could, for example, use a clustering technique. If you look here, kind of sort of eyeball it, we have a cluster around here, we have a cluster around here, and we have this tiny cluster back up here. So if we were to apply some clustering techniques first, find our clusters, and based on our clusters from, say, each cluster, we grab some at random, that would be a lot better. That way we wouldn't lose those few outliers that form their own cluster somewhere in the like away from our main clusters, right? And there is lots of different techniques for this. So I think in this specific example, I applied cluster centroid. So it does clustering. It finds their based on where the centers it thinks it is. And again, I applied a 2-to-1 ratio for my final desired outcome. So I'm getting a 10 purple points and 5 yellow points distribution. This one is, if we were to train a classifier on top of this, and I didn't do it in here because we're going to go over a much more elaborate notebook soon, I would get a much better result because I haven't lost the representation of these guys up here, and I have pretty good representation from all these parts. Now, if this was a real case, imagine each one of these maybe was 100 points. So it applies to a larger data set as well. Again, this drawback is that you could lose information if your clustering loses information, but it is a lot less likely to lose your outliers or lose some of your clusters because you're applying clustering first. So it is an improvement on top of undersampling. Next, I'm going to go over the ensemble of resampled datasets. This is completely different than, not completely, this is different than undersampling or oversampling. This is basically a version of undersampling where you're going to keep all of your minority sets. So if you look at all these 9 datasets that I created, all of them have all of the minority dataset. But from the majority dataset, I picked, again, 10 in this case. You pick certain ratio of the majority. So you don't keep all of the majority, which is all these purples. You keep some of them in each training, in each created dataset. And then you train your classifiers on top of each one of these separately. That way, in this case, we're going to have, say, at least 9 classifiers if we do 1 classifier per each one of these. They all know about the minority class, but they all know about different set of majority class. And that would give them the power of hopefully knowing or learning different things about them. Or if some of them are learning or mislearning, the other ones collecting them when we create an ensemble of all these models. So this is useful if you can, or if you want to create a more robust model by using ensembling, or if you want to get a more, say, precise model by doing boosting. Actually, you couldn't use it for boosting. Never mind, I'll take that back. So for ensembles, if you want to just ensemble a bunch of models together, this is pretty helpful in a case that you just create random representations of your majority class, keep all your minority class, train models based on each one, and then you create an ensemble of all of these models that came out. And hopefully that overall ensemble can give you a fairly reasonable outcome out of this. Again, this is also fairly, not fairly recent, but it is recent and there are papers on it. So if you just look it up, you will find papers that go into the details of mathematics of how to implement it. And I believe Scikit actually has, Scikit has ensemble, so it could help you with implementing it as well. In terms of drawbacks, of course, it has the computation time. Now, instead of training 1 classifier, we're going to train 9 or however many you decide to train. And it increases your model complexity in general. So if you need to explain your model, for instance, it's going to make it a little bit more difficult in terms of explainability or in terms of understanding your model and getting to your final optimal case. Now, it probably lets you create a better optimal case at the end, but it makes it more complex to get there. So this is another way of dealing with doing the data wrangling and dealing with your imbalanced data set. And each one of them, again, have their own pros and cons. So it's not like this is better, this is the best, or something else is the best. Based on your data set, based on what your outcome is, your business objective is, you would want to play with different ones to see what kinds of outputs you can get. Last one, which we're going to go over it during the hands-on session 2, is called SMOTE. Now the question is, what is SMOTE? SMOTE stands for Synthetic Minority Oversampling Technique. And if you look at the right side, I can explain what it does. So in terms of just intuitively what it does, it creates synthetic data. It looks to see how your data is distributed, and it for the lack of a better word in the simplest term, guesses what the other data would have been if you would have observed some. And the way it does it is going to pick 2 points that are relatively close to each other in like feature-wise, distance-wise, and it's going to draw a line, and it's going to find a point on that line, say, okay, if I were to guess, this would probably also be of this class because it's very similar in all the other aspects, and I'm just mutating some aspects of it to not in a wild way. I'm just mutating it to stay somewhere between the two features that I know it already mapped to this class. So if you look down here, what it has done, it has created a bunch of dots for me to actually reach the 100 points down here that seem to lie pretty well between these other points that existed. So it tries to create data that you haven't observed, but probably would have been also of this class, and it gives it to you. It doesn't always work because sometimes the data that it creates is not just as simple as, hey, I'm going to guess the data that falls between these other points that I've observed, and it's there. It's of that class. But a lot of times it does work pretty well. So it's a good technique to look into if you absolutely have no way of gathering more information, and simple undersampling or undersampling with clusters is not really all that helpful. In terms of usefulness, it helps you increase your precision, but it comes at the cost of recall. So keep that in mind. If that is the objective you're going for, if you're trying to increase precision and you don't necessarily mind the recall, lowering the recall by a little bit, just keep in mind Smote might be one of the very good choices to look into. Now, that's the end of the techniques that I want to cover in terms of data wrangling. These are techniques that you can apply to your data, and I'm just going to go over them real quick again to remind you, to change the distribution of your data in a way that's more helpful, in a way that's better suited for training classifiers or regression algorithms on top of it. In this case, I'm talking about classifiers. Again, we talked about oversampling. We said it's good for algorithms that are sensitive to to skew in the data distribution or the balance within your data. We said it can overfit. We talked about undersampling. We said that it's good if you have a large enough data set that losing some information isn't terrible, and if your majority class is fairly uniform, so just randomly picking doesn't lose too much information. But we also talked about the risk that you actually are losing information, so that might not be good. It might help you generalize. It might not help you generalize if you lose critical information. Then we try to address the fact that we lose possibly some critical information by using some clustering on our undersampling technique. So we cluster our majority class first, then we pick randomly from each cluster. It performs significantly better, but again, it has a similar issue of you pick how you want this ratio of, you pick basically how many points you want to choose when you're undersampling. So if you go too low, you might lose important information. Otherwise, you're probably fine. Then we looked at the ensembles. This was a different technique. This required also slightly different technique in terms of modeling, but it could give you a more robust model. Of course, comes at a cost of complexity and time, compute time, but could be a nice way of addressing it. And it kind of lays out the part that you're not stuck to one of these techniques. You could apply multiple techniques and train different pipelines and converge them eventually, ensemble them. And finally, we talk about Smote. And I believe there are, actually, I'm sure there are enhanced versions of Smote as well, but this is just basic Smote. And the way it does, it's going to try to guess where other data would have been that would belong to your underrepresented class, to your minority class, by just drawing a line between your closest points in terms of like distance in features and trying to add more data between them. And we talked about its pro and con, which is it increases precision at a cost of lower recall. So that's about it for data in terms of data wrangling. I'm going to go real quick over some aspects of how you can think about your problem differently, how you can set up your problem in terms of models and setup. but not much detail, just so you have it in the back of your mind. And if you're trying all these techniques and it's not necessarily working, it might just ring a bell one day in your head. It's like, hey, let me try this other thing that we talked about. So let's just go over it real quick. First things first, in terms of problem setup and models, make sure you're using the right evaluation metric. I talked about this a little bit earlier, but in cases where you have an imbalanced data set, more often than not, accuracy is not what you're looking for. And we gave the example of cancer, right? If you have a model that just guesses nobody has cancer, just hard-coded, nobody has cancer, probably in terms of accuracy, it's pretty right. Statistically, number of people who have cancer is fewer than those who don't. So statistically, it probably has good accuracy, but that's completely useless case test, right? You probably want a test that identifies everybody who is going to have cancer, and maybe some who it thought they do, but they don't. And then you just send all these guys to a more expensive screening. So point being, pick the right metric for your problem and try to optimize for that. And that's super important, because if you pick the wrong metric, you're going to solve your problem, you're going to optimize it, but it won't necessarily be what you want. So maybe you don't see the problem with the imbalance because you're looking at accuracy. But once you switch to recall or precision, or F1 score, which is the harmonic mean between the two of them, so it kind of sort of brings them together as one metric, then you start noticing that, hold on a second, this is not necessarily as good as I thought. Or I haven't mentioned here, but if you're looking at the area under curve for the RSC curve, that could show you pretty well as well. I'm just going to go real quick over what recall and precision are, because I think these two are the most important, not the most important, but some of the more common ones that people use. And you could use it in your problems as well. So precision is how much of the, so precision is your true positives over true positives plus false positives. So it's the case of how many of what you identified, how many of the ones that you classified as your target class was actually in that class. So how much of what you got was actually useful. So I don't know, if I said 10 people had cancer, 8 of them had cancer. So that becomes your precision, how precisely it identified people. And recall is on the other side of it. Recall is of the people who actually had this disease, how many of them did I got successfully? And it doesn't necessarily care about the ones that I misidentified as having it and they didn't have it. And I'm trying to put these in simple terms. So in a case of, say, I don't know, cancer test, probably recall would be the right thing to look into. Or if you were going to send a offer out for thinking people who are going to churn, you want to identify everybody who's going to churn. And that's fine if you identify a few people who are not going to leave the company. You gave them a nice offer, a better offer. In exchange, you have sent an offer to everybody who was likely to leave. So look at these, and then in cases where both of them are important, you can look at F1 scores. That's the harmonic mean between the two. That's kind of lumping them together. So if you optimize for F1, you're basically trying to optimize for both of them and at the relatively equal importance. Point being, you got to understand why you're picking which one of these, and you need to understand what your business case is, so you pick the right metric and you solve for that. And if you pick the wrong metric, you might not even see the problem that you're having with your imbalanced data set. Next thing is know your algorithms. Obviously, try lots of different algorithms, try ensembles, try bagging, try boosting. Some algorithms are more susceptible to skewing the data than the rest. Some suggestions that you could look into if you have imbalanced data sets. Of course, this is not everything, and this doesn't include if you're going to create ensembles of these. But you could look at XGB boost, XGB for sure. Usually does pretty well. You could look at AdaBoost. That also usually does fairly well. You could look at gradient boosting, and you could look at random forest. These are, again, not the only things, but these could be good starting points to look into your imbalanced data set that hopefully you've adjusted before getting to this point. because this would be the analyzed part of the ladder. In the organized part, you got to clean your data. So keep in mind, the algorithms could make a difference. Then the next thing is using the right loss function. This is a suggestion I have in case you're really stuck and you have to use a specific algorithm. Say, I don't know, for explainability, you're forced to use random forest so you can know the importance of each. This is a super basic example, but so you can know the importance of every feature. Maybe you're stuck with it. In that case, you can try to play with your loss function. You could try to create your own loss functions that penalize it more heavily for getting your minority class wrong than it would for getting the majority class wrong. So you could make it significantly more expensive for it to miss the minority class. And you could create your own loss function, and a lot of algorithms, say the SVM, support vector machines, LDA, they have already versions of them that have implemented this different penalty for them, this different kind of loss function. So you could look into using those if you're forced and stuck to use a specific algorithm. Otherwise, of course, play with different algorithms as well. And finally, if you can, look at your problem differently. Anomaly detection, change detection, they are both their own fields of study to a point that they even have their own terminologies defined. So if you could frame your problem as a case of you're trying to look for an anomaly in a specific behavior, or you have a normal baseline and you're trying to detect changes in it, you could actually use lots of the advancements that have been done in those two fields and try to leverage those for your problem. Now, those are completely out of the scope of what we're going to talk about today, so I'm just putting them out there, like I said. So one day, hopefully, they ring a bell in your ear and they might click. Like you might be trying to solve a problem, and you might think, oh, wait a minute, we talked about anomaly detection. Let me see. This sounds like we have a norm and we're trying to find anomalies in it. I don't know. We're trying to find hairline cracks and steel production. That most of the times is fine. You're just looking for anomalies in there. So I talked a lot, and I gave you guys lots of information about how you can do your data wrangling, how you can look at your problem differently. And each one of these things that I went over in like 5 to 10 minutes, you could have an entire hour dedicated to them. So I understand that was lots of information, but hopefully I built enough intuition for you. So when you look at your data set, you kind of have a feel at least of what techniques to try. And it's not just a gut feeling, it's more of an educated guess that, okay, based on these things, I have some random outliers out there. I want to do my, I want to do my KNN first, find my clusters, and then from those randomly pick, etc. So with that, I'm going to point you guys to a hands-on lab that you can do. I'll walk you guys through it real quick, but the lab is there. You can use it and you can go through it at your own pace and run it as a Jupyter notebook. So where can you find it? The way you found me. So developer.ibm.com has a ton of good material for you. I'm going to go over a notebook that's called Predicting Fraud Using Skewed Data. So you can either go to developer.ibm.com and type skewed data or the whole name, and you'll find it. Or this is the link for it, developer.ibm.com/patterns/predicting fraud using skewed data. For the sake of this lecture, I'm going to open it up from developer.ibm.com. Wrong place. Oh. Developer.ibm.com, and then let's just search for skewed data. And there you go. First one is the right one. You can just open it up. Also, hint, the security conference I talked about, it has a banner up here. Definitely register. So here's the code pattern. And we call these educational articles that have code and video with them code patterns. It goes over a summary of what's the problem you're trying to solve. We have historical data and based on some credit card transactions, and we're trying to find fraud transactions, like fraudulent transactions in them. It has the description of where the data set comes from. This is a legitimate data set. And why is this problem important? Obviously, fraud costs credit card and debit card companies lots of money. So finding them and detecting them in time could save lots of money. And beyond that, it goes over the flow of how things are set up. You could run this locally on your Jupyter notebook on your laptop, but if you want extra compute power, if you want to see how things run, or if you want to just run it on the internet, on the cloud, and collaborate with someone else, you could follow the flow that it has outlined for you here. So all you do is you log into IBM Cloud, you create a new Watson Studio project, you create a new notebook, you add your data, and then the rest of it is written in the notebook. So I'm going to show you how you do it. You basically go to cloud.ibm.com. For the interest of time, since I have only 10 minutes left, I'm going to speed up through this parts. But you go to cloud.ibm.com. Once you create your account and logged in, you type Watson Studio in the search, and then you can click on a new Watson Studio that comes down here. You create a new instance, you give it a name, and then you're good to go. So I'm already in my instance. Actually, yeah, I'm in my instance. And once your instance is ready, you go to your instance, click Get Started, and that should take you to your Watson Studio online platform page. It's going to have a couple of small cards that tell you what's where, so that's a good thing. And then beyond that, you have your project. You can click on your project and add your notebook and add your data to it. I already added the notebook, I already added the data. So if I go to assets, I see my notebook and I see my data added. So let's open up the notebook and take a quick look through the notebook to at least describe what's happening in the notebook. So while it's coming up, in this notebook, we are covering just you're pulling the data in, you're training 3 different models based on that, 3 different algorithms, and we're seeing how they're doing by comparing their F1 score. Then we're going to go further down and do some undersampling and see how undersampling impacts our F1 score. And then we go even further down and apply SMOTE and see how SMOTE impacts our F1 score. So knowing that there are those 3 parts to it, let's look at it real quick to see how things line up. The setup is setting things up and doing your imports. This step tells you to click here, go to your data, pick your data that you added after you upload it, and then do insert as pandas data frame. It inserts something that looks like this. And then from there, it gives it a data df name, but for consistency, we rename it to df for data frame. From there, we do our regular exploration as if this is the first time we saw the data set. So you would do some description to see where the means are, kind of get a feel of what the distribution in it is. Then we do our histograms. So we plot it, say in this case time, to see how things stack up. And of course, we wanted to know how our class distribution, which is our label, stacks up. So we're going to do a histogram of that. We see this and we're like, this is odd. I have 50,000, almost 55,000 of one class 0, and I have, I don't know, a sliver of class 1. So something we need to look into. Then we're going to do a plot of each class separately. And we see, yep, we got 50-some thousand of one, and we got only 80 of the other. So not all that good. That's something we need to look into. This acts as an amount, so it shows some we are hopeful. There is some possibility to actually derive insight from it. Then we go further, actually do the size to see how many of them we have exactly now that we're suspicious that they're off. And we see, yep, for every 550,000 of them, we have 100 of them. So for every 570, we have only 1 case of fraudulent. So this is heavily skewed. So I would assume that now when we train our classifier, it would tend to miss some of the ones. Now, we just do some histogram here to see how things look like, get a feel for our data. Of course, you also would want to, in this case, we know it's fine, but you would want to do some joint plots to see if there is any cross dependencies, any correlation between the classes, because it would, again, throw off some algorithms. I tried to make that plot, but it looks super tiny, and it doesn't show. I did a quick look. I didn't see much correlation between the data that I plotted, but I also should have plotted a different plot for that. But nonetheless, you can plot them, joint plot them, and see how they look like against each other, do your data exploration. And at this point, you would want to do, and these are a couple of those, they're magnified. You want to see how is the spread of fraud versus non-fraud based on your features. So randomly, we pick some columns and we plotted them to see if there's any useful insight coming out of them. And we see, yep, there is a good spread between them. So we could possibly either use only these columns if we really want to get crazy, or at least to begin with, we do all the columns. So we did some spreads, we see some good results. And then we start our process of training models to see how things look like. So first step, you do your train test split. You're doing 70-30 here. You can pick whatever makes sense for you. And then we train our models. So we're training a random forest classifier here. And we see that it got an F1 score of 83 by just whatever data we had. And like I said, it's got good precision, but not a terribly good recall. It's missing a bunch of the one class. It's skewed, as expected. Even though it's terribly accurate, it's like 99.9% accurate. But I mean, that's not not the metric we care about, and you should be cautious of that. Next, we're going to try gradient boosting here. Same thing. We'll do our training based on all the data, and we see, okay, it's actually doing better. Gradient boosting seems to be a little bit less sensitive to the skew in the data. Okay, that's good. And then we go with the final one with XGB, extreme gradient boosting, and we'll see what that gives us. And as expected, it has the best F1 score, 85. And here we're also looking at the AUC, the area under curve for the RSC curve. So far so good. We know not the best. These aren't hyperparameter tuned, but a rough idea of what we can get with it is about 89%. Now we're going to start selecting some random variables. We're trying to do some rudimentary dimensionality reduction by just picking these columns to see if it makes any difference. So we just pick some of the columns. Again, we train all of our 3 algorithms. The first one has some improved score. Sorry, it has reduced score. It's doing worse. Also the gradient boosting has a reduction in score. It's now at F1 of 77%. And XGB is slightly higher. But nonetheless, what this should tell you, and we didn't do it here, is that just randomly picking columns is not a good idea. Maybe you should go look back at the random forest to see what columns it thinks are important and at least start from those. We get those, and then we're going to start our undersampling process. So we do a random undersampling process. We're going to, again, do our train test split, keep some, drop some from our class 0. We're going to keep 10% of it. We're going to keep all of our class 1. And we're going to train our models based on that. We see that our F %5 for the XG boost. So all 3 actually did significantly better by just us dropping 90% of the higher with the overrepresented class. Now, of course, you would want to look again more into this, try to do some clustering, maybe try to undersample one, oversample the other. But this just goes to show you what function calls you need to make to get to where you want. And some examples of actually increases accuracy quite a bit. We went from 77% that we had to that now 95. Then we go over SMOTE. For this one, you need a different library. It's called imblearn. It's specialized for imbalanced datasets learning. I created all those graphs using this, the one that I had in the slides, using the imblearn for resampling and then plotting it. So super useful, definitely look into it. But all we're doing is we're getting all of our data set, we're getting all of our columns, and we're going to increase our samples for fraud from 105 to 500. Not terribly huge increase. We're not going to one-to-one mapping, but we're increasing it fivefold. And again, the way it's doing is picking points. It's drawing lines between them in terms of distance, and then it's creating new points on top of those. So we create our new data using SMOTE. This is where the part that it's doing, it's refitting or it's doing resampling. And then we do our training based on that. We see our recall has gone up. We have 94% for our gradient boosting now for random forest, 91 for the F1 score of gradient boosting, and we see our recall again is 93% for the XG boost. And I know I went through this super fast, but that's because the code is there and you can go through it. The point that it's going to make is that it's some sample code for you and some on real data showing you how you would start and go through your journey of bringing your data in, exploring it, getting suspicious that you have imbalanced data sets, applying different techniques to it, and iteratively seeing how you're improving it. Again, like I said, these are basic, rudimentary, good places to get started. You would definitely want to use multiple of these algorithms. You would want to hyperparameter tune them. You would want to do your bagging and boosting and create your ensembles on top of that. So do feature engineering, feature selection. There is lots to be done here, but one problem at a time. And then in today's workshop, the problem we're addressing was just dealing with the imbalance of the data. So real quick, to summarize it, you can find this code pattern on developer.ibm.com and search for skewed data. Then we talked about different ways of dealing with imbalanced data sets. First thing we put out there was the best technique out there, industry standard. If you can, collect more data. It's usually pretty hard, but if you can, collect more data. Then we talked about some data wrangling techniques. We talked about undersampling, oversampling, undersampling with clustering. There's lots of different kinds of undersampling you can do. You can do near misses, which I don't have time to go through, with different kinds of it. We talked about ensembles of resamples. So how to create different resamples, keep all your minority class, randomly select some of your majority class, train on top of that, create an ensemble. We talked about SMOTE. We gave you example codes for undersampling and SMOTE. And we talked about some conceptual thoughts about just setting up your problem right, making sure you have the right evaluation metric, making sure you have the right loss function if you're stuck with a certain algorithm, making sure you pick the right algorithm, or at least try different algorithms. And finally, making sure that, if possible, you frame your problem in a different way where there has already been lots of academic work or even practical work there, and you could possibly take benefit from that. So with that, I know I just gave you guys lots and lots of information, but I think they're all good and useful, and they could save you lots of time when push comes to shove. So I hope at least it got you intrigued to go find more information, look on our developer.ibm.com site, we have multiple code patterns that study different aspects of this, dealing with, like they have actually codes for different kinds of doing some of these algorithms, different ways of dealing with the imbalanced data set. So hopefully it got you interested enough to go find those, look online, find research papers, read about them, and get building better models. Hopefully this was something that's going to come in handy, and I hope to see you guys in the security conference and the next sessions that we'll be hosting. With that, I'm going to call this a wrap. And if you have any questions, definitely reach out to me on my IBM profile, on my email, on GitHub, LinkedIn, and we'll connect. All right. Thanks, everyone. I hope you learned a lot and hope to see you guys soon.